just going to write it like that. Here, 1 over 1 minus lambda, that squared. When I square here, the negative goes away. 1 over 1 minus lambda, that thing squared, equals 4. They all have the same denominator. Right? They all have the same denominator. Since they all have the same denominator, I put them together. What's that, 11 of those? 11 over 1 minus lambda squared equals 4. And then now you can just kind of like multiply both sides by the denominator here, right? Multiply the left side by 1 minus lambda squared, multiply the right side by that, then divide by 4. So you should get 11 fourths equals 1 minus lambda squared. This is ugly, but it is what it is, okay? And now you take the square root on both sides. So you get plus or minus root 11 over 2. I'm taking the square root top and bottom, plus or minus, equals 1 minus lambda. And then I think my last step is I'm going to move, since this is negative lambda, I'm going to move the lambda over here. I'm going to move that to the other side. And so I get a final answer for lambda. Lambda is 1 plus or minus root 11 over 2. Yeah, same thing. Yeah. Yeah, you switch it, same.
Is that a real thing?
Yeah.
No.
But yeah, it doesn't matter if you do plus, minus, minus, plus. But on like the, in pre-cal, when you had like the trig formulas where you would have like sum or difference, like plus or minus, and then the formula was minus plus, that has to be that order. Like you have to pay attention. Okay, we have a lambda, right? If we have lambda, we have x. If we have lambda, we have y. If we have lambda, we have z. And we go plug those in, and we're going to get an answer, okay? I'm not going to do it. I'm going to have the computer do it for us in a second, all right? We have to take one thing into consideration, right? We were saying lambda wasn't 1. We need to go back and look at if lambda is 1 now. Do y'all agree, though, that I have answers, right? I actually have answers. I can figure out what x, y, and z are. Okay, so let's now look at lambda being 1. Suppose lambda's 1. I'm going to go back to this equation right here. If lambda's 1, what does that equation become? X minus 3 equals x. Bless you. And then you can just subtract x from both sides and you get negative 3 equals 0, which isn't true. So we can't let lambda be 0. I mean, can't let lambda be 1 because then the first equation doesn't make any sense anymore. All right? Which means the only answer we have is the one we got, the plus or minus 1 plus or minus root 11 over 2. All right, so now if you know how on my notes I've given you my notes in both like a PDF format, but then also in the other format you can open with the player. I don't know how it works on the player if anyone's tried this, but at the end of all these notes, I actually wrote code to actually do these problems, all right? So the way that this works, it's a little bit weird, but when I wrote this code, it was a long time ago, and there's been some updates in the software since then, and I'm not sure how it's going to run. It ran for me today, so here's the way it works. You look here and it says, okay, do we have a function of 2 variables with a constraint? Is that what we have? 2 variables and a constraint? No, 3 variables and constraint. That's the next one down. Oh, I left my code open. Okay. All right, so here's what you do. If you have, let me close this. Okay. If you have a function of 3 variables with a single constraint equation, then the first thing you do is you type into here what you're trying to optimize. So what were we trying to do again? I've completely forgotten. Oh, it was x minus that squared, hold on, plus minus 1 plus z plus 1 squared. Okay, so you type that in, and then you put the constraint here. So the constraint was that we had to live on the circle, right? X squared plus y squared plus z squared. So you put the constraint function, okay, And then you put the constant right here. Where the hell's my constant box? Where'd it go? What the hell? Let me tab. Uh-oh. Let me redo this. Okay, I don't know where it went. So 4. So you know what I'm doing here? I'm putting the left side of the constraint equation here with the variables, and then the constant goes into this box. That's just the way I had to do it to make it work. I've got to retype this. X minus 3 squared plus y is 1 squared plus 1 squared. There we go. Then you have to go up to this top right corner and hit update, and it will run the algorithm. And then over here you get your answers right there. So look at it. This actually solves for x, y, z, and lambda. So this was our lambda, right? 1 plus that and 1 minus that. And then if you plug in, you'll find your x, y, and z, and you'll get these 2 answers. Now remember, this right here is the actual distance. So you would have to take the square root of that and then the square root of that to get the true distance. Remember we squared the distance in the beginning? But these points would be correct. So this is the point. This is the x-coordinate, y-coordinate, z-coordinate on the sphere that has the furthest distance from the point we were given. And then this is the x, the y, and the z on the sphere that has the shortest distance. Yes?
So we would have to test those 6 points that we got for the x, y, because we got plus or minuses for each one.
Well, you would have to test them all because you have to compute this before you square. So taking -3 and then adding something is different than -3 and subtracting. So you would have to check each one, which is kind of a pain in the butt. But
Plus or the minus is the square. So we still have a plus or minus inside.
inside, before it gets squared, yeah.
So we have to check the coordinates.
All right, that's it. Gosh, we're still going here. All right. So the Lagrange method can be taken even further, where you have a function of 3 variables with 2 constraints. So just think of, let's just do the problem we just had a second ago. We had a point, right? This was the point 3, 1, -1, right? And I gave us a constraint of a sphere. And I said, try and find the points, right, that are closest and furthest from this point on that sphere. The sphere was a constraint, right? I could, if I want to, add another constraint, like not only does it have to live on that sphere, but it has to live on a plane that goes through that sphere. So maybe there's a plane that cuts through this sphere, right, and creates some curve, right? That'd be a curve on the sphere. Do y'all see the plane cutting through the sphere? So figure out what points are furthest and closest to this point, but not only are you on the sphere, you're on the plane. So that eliminates our answers we just got, because the ones we just got don't have to live on the plane, right? So now you have possibly 2 different answers. So that's 2 constraints with 1 function to optimize. Okay?
Could that be a 3D shape as well? So you have 3D shape inside of that.
It's a 3D curve. It's a curve in 3-dimensional space. That's what you're restricting yourself to. Now, how do you do it though, right? Because you now have 2 constraint equations, right? You have your g, but now you have this other function, right? So let's look at the notes. Given a function f of x, y, z, subject to a constraint g of x, y, z equals k, that's what we've done in the past, and now a new function, h of x, y, z equals c. The way you do it is, you know how we were doing gradient, like the partial of f with respect to x equals lambda partial of g with respect to x? We have to do that plus mu, some other constant, times the gradient of h. I'm going to have to do an example for you to see it, all right? You're going to have 5 equations now and 5 unknowns. Your first one is the partial of f with respect to x equals lambda partial of g with respect to x plus mu partial of h with respect to x. then partial of f with respect to y equals lambda partial g with respect to y plus mu partial h with respect to y. Then your third one, then your first constraint equation, then your second constraint equation. That gives you 5 equations. You have to find x, y, z, lambda, and mu that make all 5 equations true at the same time. One problem like this is on your take-home, so I want to do one today in class. That way I can say you've at least seen this before. Okay? So I'm going to pull this one out of the book. So here's what we've got. Let's say we have f of x, y, z equals 3x minus y minus 3z. 3x minus y minus 3z. That is a plane in three-dimensional, right? This right here, it's not a plane. This is the equation of a plane, right? Equals a constant, right? If this is equal to a constant, that's a plane equation. Don't confuse this. This is a 4-dimensional picture, right? So this doesn't look like a plane. Unless I set it equal to a constant. If I let this equal a number, then it's a plane. But as a function, it's not. Okay. Now, our constraints. G of x, y. I have the constraints x plus y plus z equals 0. That's my first constraint. Oh, no, sorry, minus z. And then the other constraint, x squared plus 2z squared equals 1. I want to know the biggest and smallest this function can be if I'm constrained to a plane and a almost circle, ellipse. It's an ellipse. So we've got an ellipse, and we've got a plane. And where those two come together, that's the only points you're allowed to look at. And we want to know with those points what makes this the biggest. All right? All right, so this is going to be the left side here. This is going to be my g function, and this right here is going to be my h function. So the first equation that I need is the partial of f with respect to x must be equal to lambda times the partial of g with respect to x plus mu times the partial of h with respect to x. Let's just do that one first. Yes?
Wouldn't the intersection of those two functions either be exactly 2 points?
It could be in this example to make it an easy problem. So you could just go find those points. But
couldn't it also be the ellipse?
It could be the ellipse itself.
But those are the only things that could be with this particular one, right?
This has a free variable. Remember, this is in 2-dimensional space, it's an ellipse, but it's tubular. In 3-dimensional space, it's tubular.
Gotcha.
So it's more than just 2 points. Okay. Partial of f with respect to x is just 3, isn't it? That's nice. 3 equals lambda. Partial of g with respect to x is just 1 plus mu times the partial of h with respect to x, which is 2x. See how that worked? I just had to do partials for each one of these. I'll have to figure out what that is. Okay, second equation. Partial of f with respect to y must equal lambda times partial of g with respect to y plus mu times partial of h with respect to y. Partial of f with respect to y is -1. That must equal lambda times partial of g with respect to y, which is 1. And then plus mu times the partial of h with respect to y. There is no y over here. So the derivative of that with respect to y is 0. Third one. Partial of f with respect to z must equal lambda times partial of g with respect to z plus mu times partial of h with respect to z. Partial of f with respect to z is -3. That must equal lambda. Partial of g with respect to z is -1 plus mu times partial of h with respect to z, which is 4z. Let's clean it up. 3 equals lambda plus 2 mu x. -1 equals lambda. Ooh, that's nice. -3 equals negative lambda plus 4 mu z. Boy, this is a nice problem. Because this one right here, we have a condition right here. Lambda has to be -1, right? And if lambda is -1, then you can solve for this and you can solve for that. So lambda is -1. So lambda being -1 implies that this equation 1 becomes 3 equals -1 plus 2 mu x, which means 4 equals 2 mu x, which means 2 equals mu x. All right, that's from the first equation. And then also, this one over here, if lambda is -1 here, it's going to be negative is plus 4 mu z. Subtract, so you get -4 equals 4 mu z. Divide, -1 equals mu z. If we solve for mu, we have to divide by x, and then I have to promise that x can't be, right? I mean, that's, if I solve for mu here, I have to divide through, right, by z and promise z can't be 0. Yeah, there's just different ways you can go with this. We can solve for mu, we can solve for x. Why don't we, hold on, why don't we solve for x and why don't we solve for z? Now, the reason I'm thinking this is because if I solve for x here, I have to divide by mu, right? And then I have to say, make sure that mu is not 0. But I was glancing up here real quick. If mu is 0, well, right here, if mu is 0, then what is this saying? Lambda is 3, but lambda is -1, right? So me supposing that mu is not 0 here is going to be fine, because when I go check what happens when it is 0, I'm going to get a contradiction. So let's do that. I like that. I'm going to say, suppose that mu is not 0, right? Then I have from this one, I have that x is equal to 2 over mu. And then the other equation here is that z is equal to -1 over mu. And if I know what x and z are in terms of mu, I can go into that equation right there, can't I? I can go into this equation right here. So maybe I should be labeling this. This is equation 4, this is equation 5. So into equation 5, I get 2 over mu squared plus 2 times -1 over mu squared equals 1. That's just me replacing the x and the z. Square everything, so 4 over mu squared plus 2 over mu squared equals 1. So I squared the top and bottom here, but then I distributed the 2 through. So 6 over mu squared is 1, and then I can just kind of, however you want to think about that, cross multiply, however you want to look at it. Mu must be then plus or minus the square root of 1/6. Oh, 6, yes, yes. Thank you. Yeah, multiply both sides by mu squared. All right, we good? Okay, we have to satisfy all the equations. We know that this is satisfied. We know that this is satisfied. Right? We know that all 3 of these are satisfied. We know that the 5th one is satisfied. Right? The 5th one. Do we know if the 4th one's satisfied yet, though? We don't. Let me write something down. I'm ready to erase this. Here's what I have. X is equal to 2 over mu, but mu is plus or minus root 6. All right, and then I know that z is equal to negative 1 over mu, but mu is plus or minus root 6. Yeah? If I know what x is and I know what z is, then I can get what y is, can't I? Yes? I'll have different scenarios I have to look at, but I could say, what if this is the positive and then this is the positive, or this is the negative and this is the negative, or the positive and negative, or negative and positive, right? And just, you have to look at these different scenarios, but we should be able to solve for y on each one of them. Now, to save myself the algebra and time, I'm going to go to my calculator again that I have at the end of this section. And the very last one is optimize the function, and then you have the 2 constraint equations. So I'm going to just type this in here. It's 3x minus y minus 3z. And then the first constraint, x plus y equals 0, and then x squared equals 1. And then hope for the best here. There we go. The what? The first one is distance. No, this was not a distance problem. This was just find the max min for this function given these constraints. So let's see, are these the right things? If we rationalize this, multiply top and bottom by root 6 here, right, we get 2 root 6 over 6, and then that reduces out, right? You get root 6 over 3. Is that somewhere?
I don't think that's.
Something's off.
0.816.
2/3. Did I type it all in right? Minus 3z x plus z equals 0. Hold on, let me grab my. No. Actually, I didn't do this one. I trust the computer. Did anyone see anything arithmetically that looked off? 4, I squared, I had the 2 there. 6, root 6.
Says the mu of the lambda is the same.
Oh, you know what? Yeah, the mu. Okay, so what's going on here? Oh. X. No, that's. What the hell? Yeah, the mu and the lambda we got right.
We got the z correct. It's the y and the x.
The x and the y. Is that just another way of writing it? Hold on. Is that what? No. Why does root 2 over 3 no way look like root?
Oh, it is.
It is?
6 over 9.
don't know. Oh yeah, hold on. This is root 6 over 3. Yeah, okay, it's the same damn thing. All right, I was losing my freaking mind. It's the same number. That right there is this, and then I just rationalized, that's root 6, and then that's 3. Okay, it just looks different. It just, all right. Okay, Lagrange. There was a problem at the end of class, at the end of the last section. Hold on. There's a problem at the end of the last section. And I set it up, 11.7. This is before we had Lagrange. And if you look back in your notes or go watch the video, we were trying to figure out the max and min of this. And it was really a big problem because we had to calculate capital D. And to do that, we had to do partial. It was a mess. And I think we all kind of got to a point where I was like, you know what, we're gonna set this up. We see how bad this is, but we're gonna stop because Lagrange will be able to do this no problem. So read through this problem again. We're not gonna do the problem. I just want us to see how we would set it up. Want to find the largest, the volume of the largest rectangular box with edges parallel to the axis that can be inscribed in the ellipsoid. So we're trying to draw this box, rectangular box inside of an ellipsoid, and we want that box to have the maximum volume possible. So the way we broke it down was instead of looking at the whole box, we looked at just like in one octant, one little box. And then we said if we can find the maximum volume of this box in this first octant, then we can just multiply that answer times 8, and that would give us the whole thing. And then what we did is we established the dimensions of that box to be, this is your x is this direction, this is your y, and then your z. That's that point right there, x, y, z. And so if you want the volume of that green box, it's just x times y times z, right? And then the volume of the whole thing would be 8 times that. So if I say the volume as a function of 3 variables is 8 of those x times y times z's, if that's the volume of the box, all I need to do now is constrain that point so that that point has to live on the ellipsoid. And so I just use that as my constraint equation. And if I do that, that's it. I mean, I just set up the Lagrange. I do my partial of this with respect to y, with respect to x, equals lambda times the partial of that with respect to x. It's your first equation. Second equation. You get the idea? Yes?
For that, would you be able to set some conditions that x, y, and z can't be less than 0?
Yeah, so you would definitely want to set conditions here. X, y, and z all have to be positive numbers, right? Because if you had any of them 0, then you wouldn't be able to, it wouldn't be a box.
With Lagrange, do we need to cut it up into 8 pieces?
Well, if you want to know the true volume, you're going to need to include the 8. Well,
I mean, solve the entire thing. Treat that as R.
it's the easiest way to establish the dimensions here. This point lives here. It has an x, a y, and a z coordinate, right? If you wanted to, you could say, all right, double the z, double the x, double the y, and that would give you the volume of the whole thing, right? But that's the same thing as just putting 8 here. Is that your question?
No, sir. So right now we're just looking at shapes, and we're looking at like particular solid shapes. Is there any way, like, can we also use this formulas for like crazy geometric shapes that aren't like necessarily just these particular shapes, or just be more difficult mathematically to do?
Well, Lagrange extends into a function of any number of variables. So we're doing 3 variables is our restriction here in this class. You could go n variables, and you have a constraint equation that has those same n variables, and then you could have multiple constraints. So you have the idea of like lambda and mu. If you had 2 constraints, you could have 5 constraints, and then you'd have lambda, mu, whatever you want those to be. So it extends into higher dimensions. Hold on, time out on questions. We did not get into chapter 12, okay? So we are going to start chapter 12 next class, and this will be where we're talking about, getting into double, triple integrals. And I think it'll be a bit of a refreshing kind of like dive back into Cal 2 integration. It's pretty visual, but you are going to have to remember how to do some integration. Not crazy like toughest problems you could come up with, trig sub with all these other things. But go refresh on integration. For next class, really do your homework for 1108. Start your take home. I'll hang out for a few minutes if you have any questions. I've got a little bit of time. Now, your question? I'm going to stop the recording.
I was just going to ask, what was the meaning of the answer?
The meaning of the answer? What do you mean?